We start GeoDa the usual way, and we're going to use today a data set of, I should take this out. A data set of census tracts in Chicago with socioeconomic determinants of health, SDOH. It has, I think, 791 observations. The best thing to do is to take it from the sample data and save it on a directory, because just like last week, we will be creating spatial weights and we have to have a way to store them. So this is the base map. First step, I'm going to create my spatial weights. Of course, I already have them. So it's going to say replace, just like last week. We go to this W, weights creation, create. We pick an ID variable. That is the first one. Object ID is good enough. Queen contiguity, let's just keep it simple. So this, as we saw last week, we can have contiguity-based weights, and then we can have distance-based weights, where k nearest neighbors is a good candidate. You want to pick the k similar to the median number of neighbors that you get with contiguity. So if contiguity says on average or median about 6 neighbors, then you should, you can do whatever you want, but one good value for k would be that same median. So if the median is 6, use k6. K nearest neighbors weights are not symmetric, you can make them symmetric. That doesn't really matter that much for our purposes, but for some of the more econometric methods, it's necessary that these weights are symmetric. So that's why it's in here. We create it, we give it a name. I always try to give it a meaningful name, because unless you do a project file, which I didn't really talk about, because I don't want to make it too complicated, there's no metadata. So if you haven't made this before, it won't say that. So now we have our weights characteristics. So for example, here, the median number of neighbors is 7 for the Chicago tracts. So then if you do KNN, you would pick K equals 7 or something like that. You need weights because we're going to do spatial autocorrelation. We're going to do local spatial autocorrelation, which is this icon here. This icon says cluster maps. And when you click on it, you see there's a lot of them, because this happens to be something that I've been working on for a very long time. Most of these I came up with, so that's why they're here. The most famous one is the local Moran. This is the original LISA statistic. LISA stands for Local Indicators of Spatial Association. And that's part of my claim to fame. So this one is at the top. It's very easy. I'm just going to talk about 2. If you are adventurous, read the chapters in the book, and then you can figure out what all these other ones do. But I know a quarter is only 9 weeks, and actually only 8 weeks, because the 9th week you have to present. Local Moran, we're going to take the variable crowding. So this is a percentage of crowdedness. Yeah, I can't make it bigger. I'm sorry. There's crowdedness in a census tract. You see down here, actually, before I do this, I'm going to make a map, a box map of crowdedness. So we have some idea of the spatial distribution of this. When you do your exercise, never say, I see a cluster here, I see a cluster there, okay? Always phrase it very carefully. There might be a potential cluster. I mean, it's very unlikely that all the browns and the reds happen to be in the same general area. That's about as much as you say. When you talk about clusters, you have to do the local Moran. So you do the local Moran, univariate local Moran, the crowding. We make sure that the weights are specified. And then if you do okay, you have a choice of 3 graphs. 2 of these are maps. One is a graph, which we've already seen. The Moran scatter plot, we saw it last week. For the sake of the default is cluster map. I always go straight to the cluster map. But for the purposes of seeing how everything hangs together, I'm going to check all 3. So now when you say okay, you get 3 graphs. They're all on top of each other, so you have to spread them out. This is called the significance map. The darker, the more significant. This is the cluster map with our 4 categories of clusters. And then this is the Moran scatter plot that we saw last week. Where is it? I'm going to move it to the bottom here. Okay, let's focus on the cluster map first. Remember last week, we saw in the Moran scatter plot how there is a categorization of 4 different types of spatial association. In the upper right corner, it's above mean, above mean, so high, high. We call that high, high. In the lower left corner, low, low. Both of these we call clusters. And then in the off-diagonal elements, we call them spatial outliers, high, low, and low, high. Last week, we used the data set with 77 community areas. Now we have quite a few more, so we have a lot more dots in this graph. Okay. In the cluster map, if you click on the red rectangle, that will select all the observations in that classification. All the red ones. On the right, in the Moran scatter plot, you see that it selects many, but not all. And that's the difference between the Moran scatter plot and the actual test for local clusters, which is the local Moran. So the local Moran actually attaches a p-value on these local clusters. What is shown on the map is not the whole cluster. I'll talk about that in a few minutes, but the core of the cluster. So for a cluster means you're similar to the neighbors. So the cluster itself is not just the core, but the core with the neighbors. Spatial outlier, you're different from your neighbors. So a spatial outlier is just a core. The neighbors are not part of a cluster. In fact, they're different. So you just want a core for spatial outliers, but for clusters, you want the whole thing. And I'll show you in a few minutes how you do that. Here we have a subset of the high-high quadrant. Dark blue is a subset of the low-low quadrant. Whatever this color is, bluish, low-high, and then high-low. And if you look at the map, you see that there is a rough correspondence to groupings of like colors. Last week, I also computed the spatial lag and made a map of the spatial lags. And then you could see how similar locations were to their neighbors. I'm not going to do that this time, but you can see it. I mean, I should be very careful saying that. You can sort of see it on the map that what I select as red, high, high, actually tends to be the darker brown or the dark red surrounded by other darker browns and dark reds. Low, low, same thing. So we're in the blues. Then low, high, what we're seeing is a blue that tends to be surrounded by browns. That's a low-high outlier. And then a high-low is going to be the other way around, is a brown that tends to be surrounded by blues. Okay. So these are the 4 categories. The difference with the Moran scatter plot is that now we have significance. Okay. Now, what is this significance? It's not real significance. It's pseudo-significance, just like with the Moran's eye. So if we go to the significance map and you check the options, you see randomization. And it's the same as for Moran's eye, but now we're going to go up to 99,999. So you have to actually enter it. The other ones are defaults. So the randomization, how many permutations? Why do we do these that end on 9? Because then it's a nice fraction. Because it's this plus 1 becomes the denominator. It's the same cells, but now you have much more of a gradation of the colors. For example, these 18 here, these are highly unlikely to occur by chance. Because roughly out of 100,000 cases, none of them came up with this number. Okay, so that is within the permutation language, highly significant. So it's highly unlikely that this is a chance thing. And what you see on the map on the right is that these are in the core of what we see on this cluster map. So what I'm going to do now is in this map, or actually I can also do it in here, I'm going to select connectivity, show selected and neighbors. When you do show selected and neighbors, it's a little tricky because it's dynamic. It adjusts right away. That's why it's best to do the selection in one map and then do show selection and neighbors in another map. And it will show the neighbors as defined by the weights matrix of the cells that I selected. And what you should see is that these will tend to have similar colors. So what have I done here? I have picked the cores that were significant at the highest significance level out of 100,000 permutations. And I have selected their neighbors. And I end up with something that looks like a cluster map that I had before. Now, one thing I haven't mentioned is what is the cutoff value that I use for the cluster map? The default is 0.05. Let me turn this off and go back. So when I go in here and I select these, it shows the subset of the ones that are significant at 0.05 that are also highly significant at this other level. Now that seems to be like a roundabout way to do this, and of course it is. A much easier way to do this is to right-click on the cluster map or on the significance map and select significance filter. This essentially cuts it off what you want to see. And let's say I only want to see these very highly significant ones, and you will see the map shrink. The map shrinks such that only those very significant ones are shown. So if you go back, the map grows. And this is a tricky question because the significance, because you do the randomization for each observation in turn, it suffers from something that is called multiple comparisons. And I mean, if you've had stats before, multiple comparison is a problem, you know, and classical statistics typically takes an approach that I call instantaneous amnesia. So you forget the results that you just got and you start over and get the p-value as if that's the first time you do it. In Bayesian statistics, you actually build on previous results. But the multiple comparison problem means, in essence, that you can't trust your p-values. Okay, so what do we do about that? Well, as it turns out, for this particular application, it's not that big a deal, because what we can do is we know that this 0.05 is not really 0.05. It's more. It's 0.06, 07, 08, whatever. We don't really know what it is, and that's really impossible to compute unless you make a lot of assumptions. But we do know that it's too much. So that one way to deal with this, to not fool yourself, because you don't want to fool yourself into thinking things are clusters that are not. So you crank up crank up or crank down, depending on how you think about it, the p-value. So as we go down to 0.01, it shrinks. As we go down even more, it shrinks even more. But what we've seen is that even though these are the cores of the cluster, the actual cluster includes the neighbors. And the actual cluster, if we do the same thing here, I go to connectivity, show selected and neighbors, then you see that you actually end up with a cluster map that is larger, but not as large as the one for 0.05. So 0.05 is too much. Is 0.01 good enough? Often it gives you a good idea of where the interesting action is. If you crank it up even more, or if you look at your significance map, then you see where the real action is in these really dark parts. Why do I have these three graphs? Because the significance map as such doesn't tell you what's going on. So what GeoDa is doing under the hood, it runs the significance map, it looks it up, each significant location, where it is in the Moran scatter plot, and then depending on the quadrant that it falls into, it categorizes it in the cluster map as high, high, low, 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 high, high, low. That's what's going on behind the scenes. But then at the end of the day, we have a very nice simplification, and that's really the way I like to think about it, simplification of the spatial distribution that we see here, especially as we crank up the significance, it simplifies the map greatly. So this variable is crowdedness. It tells you essentially there is a region here with extreme crowdedness that goes beyond the tract level. It's multiple adjoining tracts. And, if you know Chicago a little bit, you know what's going on. There's a region here that doesn't have crowdedness, right? And this remains pretty much the same. It expands a bit if you go to 0.05. So this is a bit too much. But remember, this is all part of learning about the data, finding patterns in the data. And we're looking at 791 observations. If you look at a table with 791 rows, you won't see a thing. Okay? That's the power of visualization, is that it really brings out the main patterns in the data. Now, there's one more little complication I want to show you. And this is a little technical, but some of you have taken stats, so you can handle it. We have custom significance, okay? It's all about how to deal with the problem of multiple comparisons. Does anybody know one solution to that? Oh,
You can multiply your p-values by the number of tests.
that's a false discovery rate. Yeah. Oh, you divide it by the number of tests.
Like, that's, you divide your, target significance level.
Yes, right, yeah. What is that called? Do you know what that's?
Fun.
Bonferroni. So we have Bonferroni. The problem with Bonferroni is that, so if I select it, you see, what is the number of comparisons that we make? That's a big problem because we don't really know. I mean, at most it's 791, one for each location. But because some locations are so far away from each other, that doesn't really matter. And for all practical purposes, they are independent tests. So it's somewhere between, let's say, the number of neighbors and the full data set. Bonferroni overcorrects. The result is that you have a p-value. If you have a target of 0.05 overall, you divide that by 791. This is what you get. And what this will do is shrink your map to only those locations that are the most significant. And in a way, we're getting the same thing as what we did with tightening the p-value. Then there's another method that's a little more forgiving. So one thing that could happen with the Bonferroni, especially if you have very large data sets, is that nothing is significant. Because remember, these are pseudo p-values. These are not real p-values in an analytical sense. They depend on how many permutations we do. So if we only do 999 permutations, we can't show anything that has a p-value less than 0.001. So if we do only 999 permutations and we set the Bonferroni, we don't get anything. Now, getting too much is not good, but getting nothing is not good either, right? So to apply this, you have to have sufficient permutations, and you cannot have too large a data set. In fact, I'm tired, I can't remember, but you can compute what is the maximum data set for which a Bonferroni bound makes sense. Because you divide 0.05 by that number, and that should be larger than 0.00001, right? So I'm too tired to figure it out. So the second one is called false discovery rate. You see, it's a little more forgiving. It ends up at 0.013, basically, which is roughly the same as 0.01. And if we do this, then it grows again. So this is an important part of learning from the data, is that you don't just stick with what the default gives you. The default is based on 999 permutation and a significance threshold of 0.05. That's good enough as a quick first impression. It's not good enough to do a full analysis. I always go to the max number of permutations and then look at how the shape of the clusters changes as I crank down, if you wish, the p-values. So I keep tightening the criterion for what is significant, and I look at where do these clusters disappear. That means maybe they are just, by chance, more by chance than some of these others. The ones that you find at the very highest level, they're not going to be by chance. Something is going on there that reflects some systematic structure, and then the next step is trying to figure out what that structure is. And that gets us in the multivariate domain, where we looking for associations and interaction effects. If you remember when I talked about the EDA graphs, conditional graphs, we're looking for interaction effects between multiple variables. And if there are interaction effects, then maybe we can make a story as to why these places are interesting.